Good morning, everyone. I'm Kelly. I'm representing Inlecom Innovation, and I will be presenting the main outcomes of the beta version of AI simulation module. Inlecom Innovation, established in 1996 across Europe, excels in research and innovation with a notable 40% proposal success rate and numerous completed EU-funded projects with expertise in AI, digital solutions, and advanced security. So let's dive into our part of the CRM project. The primary aim of our task is to uncover intricate relationships between elemental features and lithium concentrations, marrying geological insights with advanced machine learning methodologies. The CRM-AI tool places a specific emphasis on accurately estimating lithium concentration in geothermal fluids, while ensuring interpretability in geothermal data analysis. The overarching aim is to establish a robust foundation for pioneering research in the field of geothermal studies. Right. We started examining the relationships between lithium and major cations, anions, and fluid characteristics in the liquid phase from the CRM fluid database, the Reflect database. And we finally focused on magnesium, potassium, sodium, chlorine, and calcium. So, however, since it's not the focus of this presentation, I won't be delving into the technical details of our preparatory work. Maintaining our dedication to establishing causal relationships, we adopted an innovative approach that systematically considers all 5 elements. Consequently, we started the exploration of regression decision tree algorithms, which fell into the tree-based models category. A decision tree is like a flowchart that represents a set of rules that help make decisions based on the input variables. Think of it as it is a logical framework that guides the algorithm. The nodes are the decision points within a tree. They split the data based on specific criteria, such as feature values, and direct it to different branches. So nodes help separate the data into smaller subsets, allowing the algorithm to make more focused predictions. And finally, leaves, also known as terminal nodes, are the endpoints of a tree, and they contain the final estimation. The decision tree indeed showcased high predictive accuracy in estimating lithium concentrations. Additionally, based on it, a bespoke methodology tailored for outlier detection was crafted, ensuring a novel approach to discerning between genuine outliers and between instances of inherent variance in the data. So this part constitutes the first functionality of the tool. The user has the option to either manually input the concentrations of the 5 elements that correspond to a new sample, fluid sample, or choose one of the test model samples of the CRM Reflect dataset. The tool's output, regardless of the input method chosen, is uniform and manifests in a multifaceted manner. So it first estimates lithium for specific element values. It offers transparency and understanding of the model's outcome. And finally, it provides dynamic exploration of the algorithm decision-making process. Here, as example, we have a sample taken in Denmark, which is part of the test dataset. In this sample, the model's estimated lithium concentration is 9 milligram per liter, while the measured value is recorded as 12 milligram per liter. And in the top, in the middle, by examining the explainable AI plot on the top, the 17 milligram per liter is the average predicted lithium across all the 516 samples in the test dataset, and 9 milligram per liter, the f of x, is the predicted lithium for this specific sample. Also, the plot tells us how each feature has contributed to this prediction. And as we can see, sodium appears to have the highest impact on the specific sample, and it has increased the predicted lithium value by about 9.8 milligram per liter compared to the average predicted lithium across all the samples. On the other hand, potassium, magnesium, chlorine, and calcium have decreased the estimated value. The algorithm reached the decision after crossing 17 nodes. We can see on the slides just below the explainable AI plot, concluding at the final leaf that contains 2 samples from the 2 different wells, both in Denmark. And as we see on the left, their mean lithium concentration is roughly 9.6 and 10 milligram per liter, respectively. Now, as we move the slide backwards, we notice changes in the plots, and the range of feature values expands. At node 13, we find 8 samples with an average lithium concentration of about 13. It's noteworthy that the corresponding wells in Denmark exhibit similar lithium average, while wells in Germany and France, despite sharing similar elemental values, there is an increase in lithium concentration. And this observation highlights the geographic variation in lithium concentrations, even when other elemental characteristics remain consistent. Now, this is the second component of the tool, and the focus is on exploring the interaction between lithium and the 5 elements within specified ranges or geographical regions, and it also plays the role of the sensitivity analysis. Users select a range of test set values instead of inputting specific samples, unlike the first part. As we see on the bottom left, moving the sliders for any element, the entire dataset is concurrently filtered. And this action triggers updates in the scatter plots for each element, as well as the locations on the map. And it is important to understand how the ranges of individual elements geographically correlate with one another, and how filtering one element influences the geographic distribution of the remaining elements. A pivotal aspect of this part of the tool segment lies in its dynamic adaptability, wherein every filtration of a dataset triggers the training of a new decision tree model tailored to the adjusted data range. Consequently, a fresh measured lithium versus predicted lithium plot, as the bottom right we can see, the plot is generated and providing users with an updated visual representation of the model's performance. Also, we have a new explainable AI plot, and it offers users a transparent understanding of how the model arrives at the predictions. Finally, in this section of the tool, outlier detection is facilitated by either examining new individual samples by incorporating a tolerance range, or by examining multiple new samples from a well that fall in a specific range. This is done by verifying whether the lithium concentration falls within the expected range based on historical data, and additionally assessing whether this range corresponds to the anticipated geographical region. So as an example, we adjusted the potassium slider, as we can see on the bottom left, setting the range from 0 to 3000. The entire dataset was automatically filtered, triggered new corresponding updates in the scatter plots for all the elements, and adjustments in the points on the map. To validate the accuracy of the newly generated decision tree, we review the metrics and the measured vs predicted plot. Changes are observed in the beesworm. This is on the top, the plot, indicating alterations in the importance of order features. Here, potassium is shifted to the 3rd position, while low, medium values of sodium emerge as the most influential features. Chlorine follows as the 2nd important feature, and calcium exhibits the smallest contribution to lithium estimation in this specific elemental range. Quickly, as a second example, we refined the dataset by directing attention to a specific geographical region. We selected the sedimentary basin systems. This narrowing of the dataset allows for a closer examination of potential patterns within the sedimentary basin systems, or highlighting differences between this specific region and the rest of the dataset. Finally, I want to emphasize that the observations in this presentation are preliminary and indicate examples of the functionalities of the tool, and they serve as a starting point for more extensive investigations in the near future. Thank you.